Hello, my dear students, and welcome to the start of our second lecture in this semiconductor devices module. This is our second lecture, but I can consider this as our official start of the module. As you know, the first lecture was somehow a revision lecture or on the fundamentals or the basics of the semiconductor material. Now we will start the typical title of the course, which is semiconductor devices. Today we are going to start our first device, which is, as I mentioned previously, the most foundational device for semiconductors, a p-n junction. Today we are going to illustrate the p-n junction. Actually, the p-n junction, which is lecture number 2, most probably will be discussed in 2 successive parts. In the first part, we are going to demonstrate the p-n junction semiconductor diode under what's called the thermodynamic equilibrium condition. I mean, no external bias is applied on the device. Then in the second part, we are going to demonstrate the impact of forward and reverse bias. Of course, we are going to consider it from the semiconductor perspective, because I'm quite sure that you already have studied this p-n junction device before in your electronics 1 course, but as a circuit device. Today we are going to demonstrate it as a semiconductor device. I mean, we are going to investigate the energy band diagrams, the carrier concentration, the current flow, and all this stuff. So let me first start by sharing my presentation and open the pointer. Let's start the second lecture under the semiconductor junctions, which is the p-n junction. Okay, so at the conclusion from the first lecture, we have studied that whenever there is a doping, this doping is generally reflect on the position of the Fermi level. I mean, for an n-type semiconductor material, we should expect that the Fermi level will go nearer to the conduction band rather than to the valency band, to indicate that the number of electrons is greater than the number of holes. Vice versa happen when we go to the p-type material. I mean, whenever you dope your material with an acceptor, a third group material, the valency band is going to go downward to be near to the valency band with respect to the conduction band. Now, what happens if we combine these two junctions together? I mean, you put an n-type material beside a p-type material. How the energy band diagram should look like? How we can merge this energy band diagram? Whenever you are going to make this form of merging, you should have what's called a reference. What do we mean by a reference is a layer or a level that have the same definition in both sides. So if you return back to the definition of the Fermi level, you will find that mathematically the Fermi level is the level at which the probability to find an electron is equal to half. And this happens whenever we study the Fermi Dirac distribution. You can go to the Fermi Dirac distribution and substitute E by EF. You will find that the output will be 1/2 or half. That means that the Fermi level has a constant definition regardless of its position. Accordingly, whenever we are going to merge, whenever we are going to merge more junctions or different doping areas together, the reference layer will be the Fermi level. So let's go together now and start to plot an energy band diagram for a p-n junction. So usually the procedure is constant. We will repeat the same procedure in the p-n junction, in the MOSFETs, in the BGT, in the tunneling field effect transistor, whatever the device is, the procedure is constant. So I'm sorry. Okay, what we are going to do is first let's start to plot the energy band diagram for each part of the material separately. So we have an p-type region, and we have, okay, so I think this is now much better, and we have a p-type region. For the n-type, we have a Fermi level, which is EF, and the conduction and the valency band are as follow. As you can see, Fermi level is more toward the conduction band rather to the valency band because the number of electrons is greater than the number of holes. On the other hand, the p-type material have something like that. So now the Fermi level is more close to the valency band rather than to the conduction band. Of course, the nearer the distance, the higher the doping. So whenever you increase the n-type doping, this EF will go more and more upward. Whenever you increase the p-type doping, this EF go more and more downward. So now we are going to make a combined energy band diagram. So what we are going to do, simply, my dear students, is first we are going to plot a horizontal Fermi level. And if you remember well, our first lecture, you will be quite sure why we plot this as a horizontal line. This is basically because now this p-n junction is under thermodynamic equilibrium. I mean, we did not put any type of external bias to this p-n junction. So its Fermi level should be totally horizontal. This is typically what we have learned in the first lecture. So now every energy level or energy band should be plotted with respect to this horizontal Fermi level. For example, in this n region, we have something like that. So this is EC and this is EV. And as you can see, the Fermi level is more close to the conduction band rather than to the valency band, and vice versa here. This is EV, sorry, and this is EC. And knowing that this is a conduction band and this is a conduction band, these should be linked together. And similarly here. So this is the overall energy band diagram for a p-n junction. Again, a set of conclusions can be observed. First, it's a thermodynamic equilibrium junction. So the Fermi level is horizontal. Second, due to the junction, some tilting starts to appear here. Or in other words, you can say that this energy band diagram can be classified or can be categorized or can be divided into three regions. Why do this? Because if you look to the left, extremely right region, this region, if you go and look to this region, as you can see here, in this region, it's a normal p-type material. The Fermi level is close to the valency band and far from the conduction band. Very normal p-type material. While if you look to the extremely left region, I mean this one, you will find that it's a normal n-type material. The Fermi level is close to the conduction band and far from the valency band. But if you look to this region, you will find a tilted energy band diagram. And if you remember, we say that this tilting is a sign of a potential, a sign of an electrical field. If you remember, when we studied the drift current together, we said that whenever you apply a potential to an energy level or energy band diagram, the energy band diagram is going to be tilted.
However, we did not apply any type of a potential. And you can be quite sure of that because the Fermi level is horizontal. That's why we call this potential as what we call the built-in potential. I'm quite sure that you have already heard about this built-in potential 3 years ago in your first semester in electronics 1. So this is typically the built-in potential in a p-n junction. We called it a built-in because it's natural potential. No external bias is applied to the semiconductor device. This is a naturally created potential due to merging the n-type region and the p-type region. Okay, but is this potential will produce electrical current? Let's see. Okay, as you know, this region is an p-type region and this region is an n-type region. So let me just replot the same energy band diagram but in a new clean page. So it's a very nice way to repeat the exercise. So we have this Fermi level. And let's assume that this is the N and this is the P. By the way, in the presentation, I make it vice versa. Of course, this is typically the same. Or let's do it like the presentation. So let's say that this is N and this is P. Of course, you can do it either this or that. And then in this case, you will have here, this is the N. So this is the conduction band. This is the valency band. And that's the other way. And you can, please don't get confused. You can plot it either PN or NP. Both will result with the same output. So first we divide this into 3 regions, if you remember. So this is a typical p-type region. And this is a typical n-type region. So this p-type means that you have a lot of holes and minority electrons. So by the way, please be comfortable and be adaptable with this terminology. The higher number of carriers we call the majority carrier. So in the p-type, the majority carriers is hole and the minority carriers is electrons, and vice versa while we are talking about the n-type region. So we have a lot of electrons, so this is the majority, and we have a low number of holes. So if we examine together this depleted region, the region in between where we have this tilting in the energy band diagram, and I told you, please, my dear student, let's examine what is the direction of the electrical field. I mean, how carriers should move. Okay, you will tell me, okay, this is the drift. So if we have an electron here, this electron will tend to have a minimum potential. So it will start to move and go there. So this is the direction of electrons. If there is a battery and the positive terminal of the battery is here. So electrons are connected to the are attracted to the positive terminals. Similarly here, if you have a hole here, and please don't forget that the whole energy increase downward. So in order to get a minimum potential, hole will move like this. And as if there is a negative terminal of a battery in the left-hand side direction. Okay. So electrons shall move from the left-hand side to the right-hand side. And holes shall move from the right-hand side to the left-hand side. But here, electrons are minority. And here, holes are minority. So first of all, this current is a minority current. I mean, a very few amount of electrons and holes are going to move either this or that. And accordingly, you should not expect a very high current. This is the first observation. The second observation is You have electrons who are moving from here. Oh, sorry, you have electrons, yes, who are moving from here to there. But this is the drift current. Please don't forget the diffusion current. Do we have diffusion? Of course. Why should we have diffusion? Because here you have a huge number of electrons. And here you have a very few amount of electrons. So based on the diffusion theory, electrons will diffuse from the higher concentration to the lower concentration. So this diffusion current will work again as a drift current. Similarly here, you have a huge number of holes here and very few amount of holes there. So holes will diffuse in this direction, which is again the drift. So totally, the total current should be equal to 0. And actually, this is 100% makes sense, as this device is not connected to any external sources source of potential or of electrical field. So logically speaking, the electrical current should be equal to 0. And we already mentioned that whenever we say that this is under thermodynamic equilibrium. For example, you have a piece of diode. So do you expect that if you collect this diode by your hand, you will find a current through it? Of course not. There is no potential source. Whenever there is no potential source, no way there is no current. So that means that the total electron current is equals to 0, because the drift current will going to be cancelled by the diffusion current. So we have a diffusion current here. And similarly, we have a diffusion current there. That means that the overall current flowing under thermodynamic equilibrium is equal to 0, which is, again, typically makes sense. So let's go back to the presentation and open the pointer. So this is the separated N and P. Whenever you combine them together, you will have something like that. We call this is a normal P-type region. This is a normal N-type region. And this region, where there is a building potential, a natural building potential, we call it as the depletion region. And also, I am quite sure that you hear this term before. So this depletion region is the region at which there is a drift, a natural drift or a natural building potential. And as I mentioned, as far as we are under thermodynamic equilibrium, then please expect that the total electron current or the total hole current is equals to 0. As I just described, you have an electron current moving in this direction, but you have a diffusion current moving in the other direction. Similarly here, you have an electron current, a drift current moving in this, and a diffusion current moving in this direction. So the total current is equals to 0. Now, for using this equation, we can make a very important observation. Of course, these are two identical equations, so you can use any one of them in order to make the guess. But before using these two equations, let me ask you a question. Is it possible to plot the carrier concentration in this p-n junction? What I mean by carrier concentration is the electron concentration N and the hole concentration B. Is it possible to plot this carrier concentration? Let me show you how we can plot the carrier concentration in this example. So this is typically a p-n junction energy band diagram. And what I'm asking you to do now is to plot the electrons hole concentration across this device. So what we are going to do, my dear students, is that we have this x-axis, which is corresponding to the position, and this y-axis is corresponding to N and P. I will plot N in black and P in blue. So let's do it. Let's start for N, for example. Again, we have here 3 main regions. we have this pure N material, this pure P material, and this depletion in between region. So let's start with the N region, for example. So for the N region, as you know from the revision lecture, whenever it's an N region, then the number of electrons is directly equals to the donors, which is ND. And of course, the number of holes, if you remember, I'm sure you remember, P equals Ni squared over ND. However, in the left-hand side region, now the majority is holes, so P is equals to Na, and N is equals to Ni squared over Na, which is a minority. So in the right region, N is large, N is equals to ND. So we have some, for example, value here. This is called ND. However, in the left-hand side region, N is a minority. So this value, for example, called Ni squared over Na. And of course, you have a continuous function in between. On the other hand, you will have here value called Na. And here you have value called Ni squared over Nd. And in between, there is a connection like that. So this plot represents the variation of holes and the variation of electrons across the device. And in order to make a standard terminology for this, we will make it like that. So please concentrate. We will call this N node. What is N node? N is a number of electrons. The small n is an n side. And node, if you remember, this is due to equilibrium. So this will be called P N node. P, because this is holes, and the N region at thermodynamic equilibrium. And similarly, this is called P node, which is of course equal to Na. And similarly again, this is called NP node. So these are the four main concentrations evaluating a PN junction. And of course, PP node equals to Na, and NN node equals to ND. And you can calculate the minority using zero mass action law, Ni squared over Na or Ni squared over Nd. So now we have two facts. This carrier concentration, and also we have another fact, which is the equation saying that the total electron current is equal to zero. I mean the drift current and the diffusion current is equal to zero and under thermodynamic equilibrium, and the diffusion current and drift current for holes is equal to also to zero. How we can use these two equations or these two facts together? Let's see. Okay, so I'm just going to rewrite the equation mentioned in the slide. I will consider, for example, the equations for holes, saying that the total hole current, which is the JP, is equals to the drift hole current, which is equal Q, the charge, times P, which is the number of holes. By the way, Q and the letter small e both are identical. So maybe in the slide I write it E or Q, both have the same meaning, which is the charge unit, which is 1.6 times 10 power negative 19. So whenever it's E or Q, small, both are equal. Q, E, and then we have the mu P term, which is the mobility of the holes, and then we have the eta term. If you remember, whenever there is an eta, there is a drift current. Minus Q dp by dx. This is the general whole current. This is the term represents the drift, and this is the term represents the diffusion. Now, this overall current is equals to zero as far as we have thermodynamic equilibrium. So the whole current is equals to zero. Accordingly, you can say that Q P mu P times eta is equals to Q dP by dx. Very straightforward. Q can be cancelled with Q. And if you remember, my dear students, the term dP over mu P was given by Einstein coefficient, that dP over mu P equals KT over Q. Or if this KB comes here, so you will find that KB Q over KT times eta, which is this term, equals to 1 over B dP by dx. This is the equation. Okay, let's proceed. So the equation we have is Q over KT times eta equals to 1 over P dP, sorry, dP by dx. Okay, what is eta? Eta is the electrical field, and its unit is voltage per meter, if you remember, from the electromagnetism maybe. So this eta can be written as dV by dx, because the electrical field is a differentiation of the voltage with respect to distance. So we have an equation called K QKT dV by dx equals to 1 over P dP by dx. So this is typically the equation. You have two sides with differentiation. Then you can calculate now the voltage. If you make integration to both sides, you can calculate the voltage. But the question is, which voltage we are going to calculate? So let's turn back to this slide. We only have one voltage in this schematic, which is the building potential here. The voltage here is zero, so you don't have integration. The voltage here is zero. You only have voltage here, which is the building potential. So you can calculate the building potential here by simply say that by the integrating both sides from 0 to V node to V, delta V is equal to integration 1 over P, and then the integration here is dP. What about the limits of this integration for this dP? So let's turn back here. You are now integrating in this region. That's right. So what is the limit of the P in this region? It's typically this, from PP node to PN node. So this is an integration from PP node to PN node. Of course, you know both values. So you know that PP node is NA, and you know that PN node is NR squared over ND. So you can substitute here and there. Of course, I'm not so interested with mathematics. I'm just showing you the procedure. I will not going to ask you about the division, but I'm just describing to you how we calculate the building potential of a PN junction. So let's turn back to the presentation slides. herein. So this is the carrier concentration as I just plot, and this is the equation we have concluded together, and this is the limits of integration, as you can see. And using this equation, you can calculate a term that describe the building potential, which is kT over Q, which is, if you remember, the thermal energy, and this value is equals to 25.9 milli electron volt whenever the temperature is room temperature, ln Na and D over Ni square. So using this relation, you can basically say that the building potential of a semiconductor p-n junction depends on, first, the temperature. So whenever you change the temperature, you should expect that the building potential increase. Second, the doping, the Na and D. And third is the intrinsic concentration, which is the material parameter. So if you remember, my dear student, when you were in year one electrical, they told you in the lab that the building potential for a silicon diode is 0.7 voltage. However, when it's a gallium arsenide diode, for example, it turns to be 0.9. Why? Because simply you are changing Ni. So whenever you are changing the intrinsic concentration, I mean, whenever you are changing the material, you should expect that the overall building potential will change. Similarly, if you have a silicon p-n junction, but you change the doping level, I mean Na and D, then also it will change. Again, if you have a silicon p-n junction with a certain doping fixed, but you change the temperature, then you should expect a change in the overall building potential. So this is a very, very important equation, my dear student. You should know it well. Again, I'm not going to ask you about the revision, but you should understand this equation well, and you can substitute to calculate the building potential for different p-n junction. Okay, let's go to a next step. What is after the building potential? Okay, so what is after the building potential? Let's turn back to this energy band diagram, and let's start to discuss why we call this region as the depletion region. Depletion is an expression from the verb deplete or depleted, which means that nothing exists. So why this is an empty region? Of course, when I say it's empty, I mean it's empty in terms of carriers. So let's discuss. So if I told you, my dear students, now please observe my pointer. Is there any probability to find an electron in this stage where I'm mentioning my pointer? I believe your answer will be no, because whenever there is an electron here, it is automatically will going to drift and go to this side. It's a sliding space. So whenever you have an electron here, it will go typically in this direction till this area, this sliding area, is empty of electrons. Similarly, whenever you have a hole here, this hole will automatically slide downward, or sorry, slide upward and go here, because again, the energy of holes decrease downwards. So holes are going to slide in this direction till it reaches this point. Accordingly, at thermodynamic equilibrium, there is no probability to find carriers in this area. What I mean by carriers is either free electrons in the conduction band or free hole in the valency band. Accordingly, this region will turn to be a depleted region from carriers. That's why we call it the depletion region. And this is actually a very important point in what's called the capacitance of a p-n junction, which will be the last slide in this lecture. Because as you can see, and based on the observation we just concluded, no free carrier exists in this region. And if you remember, my dear students, our definition for insulator, we say that insulators are the materials which has no free carriers. So this in-between region will tends to be like an insulator because there is no free carriers in this region. Accordingly, you have here a region, a p-type region, where there is a huge number of holes. And here you have an n-type region where there is a huge number of electrons. But in between, you have a depleted region. You have an insulator, which is typically, my dear students, a paraplate capacitor, a conducting material, an insulator, a dielectrical material. That's why in the p-n junction semiconductor diodes, we have what's called an internal capacitance. In other terms, they call it parasitic capacitance. And this is, by the way, one of the most important topics whenever we start dealing with transistors, and namely the MOSFETs. So this is the depression region. Again, as I told you, the total current is equal to zero. And current is charge. As you know, current is the flow of a charge. Whenever I told you that the total current is equal to zero, that means that the total positive charge is equal to the total negative charge. I mean, the total electrons that flow from the left to the right, the total electrons that drift here is equal to the total holes that drift there. Okay, perfect. Then how we can calculate this total charge? Let's see. Okay, so I'm going to use not this one. Okay, so let me draw it from scratch, no problem. Okay, so basically we have N region and P region. So let me separate them by this line. This is the P region and this is the N region. So in this period, of course, there is a formula over here, and then this is the P region, and this is the N region. And this is how we link them together. As you can see, the depleted region, which is the region where we have this drift, is actually a border region between the N and the P. So it has some region from the N region, which we will call it Xn. So Xn is a part of the depression region related to the N side. And Xp is a part of the depleted region related to the P side. And we will call the overall width of the depression region W. So W equals to Xn plus Xp. So great. Then herein we have some electrons which move in this direction, and we have some holes which moves in this direction. How we are going to calculate this total number of electrons and this total number of holes? Okay, so as you know, the total, the hole concentration is called Na, and the electron concentration is called Nd. As you know, this Na, if you remember, its unit is centimeter power minus 3. So this is charge per unit volume. In order to calculate the total charge, you should multiply this Na, this concentration, by a volume. So what is the volume of this charge? Its volume is Xp, which is the region in the P side, times the area, the cross-section area, A. This, of course, times Q, which is the unit charge. This should be equal to what? To the total N charge, which is again Q times Nd times Xn times also A. Of course, Q will be cancelled with Q. A will be cancelled with A, and then you have the very important equation saying that XP times A equals to XN times ND. This is a very, very important equation. Why this is a very important equation? Let me return back to the PowerPoint slides. Okay, as you can see here, this is the sum up equation. XP times NA, of course, we use the term XP node to indicate this is again under thermodynamic equilibrium, times NA equals XN node times ND, times ND. So why this equation is very important? Because XP will be equals to XP will be equals to XN if and only if NA is equals to ND. But if NA is much greater than ND, if NA is much greater than ND, then you should expect that XN will be greater than XP. So it's inversely proportional. So the distribution of the depletion region between the N side and the P side, which is XN and XP, depends on the ratio between the doping in the A side and in the P side and the doping in the N side. And of course, as I mentioned, XN XP node plus XN node equals to W. Okay, then how we are going to calculate W? This is a typical equation for W. Let me read it. Of course, let me first tell you that you don't need to memorize this equation. This equation will be given in the formula sheet, so don't worry about it. But I will tell you now where is the trick. W equals 2. Let me open the pointer. W equals 2 epsilon. If you remember epsilon from the electromagnetism course, epsilon is a permittivity and equals to epsilon node, which is the vacuum permittivity or the air permittivity times 2 epsilon r, which is the relative permittivity of the material. Of course, this will be given. So 2 epsilon over Q, Na plus NAD over NAND times V node. V node is a building potential. We already have an equation for V node, which is this equation. And NAD, NA and NAD are the potential. So this is the equation of W. And this is the equation for XN, and this is the equation for XP. Of course, if you sum these two equations together and make common denominator, you will get up this equation. But where is the trick, my dear students? In the final exam, in the unseen exam, or maybe even in the in-class test, I will give you this, for example, W equation. And I told you, please calculate XN. And I will not give you this XN equation. So I will give you only W. And I will tell you, please calculate XN. So you will raise your hand in the classroom and tell me, doctor, please, you did a mistake. You give us the equation for W, but what you are requested is the XN. I will not reply. Why? Because you have this W equation, but you have another two equations, this one and this one. So knowing NA and ND, and knowing that XN plus XP equals to W, you can easily calculate XN and XP because these are two other equations. So these are the only two equations in this lecture that I will request you to memorize. XN plus XP is equals to W, which is something makes sense and logic, and XP times NA equals XN times ND. So you just need one equation out of these three, and you can directly calculate the two other parameters using this two equations. So this is basically a direct substitution problem. Whenever you understand well how you can substitute in these two conditions. Okay, so this is of course, as I mentioned, this formula will be given in the data sheet and you don't need to memorize. This is the termination of part number 1 in lecture number 2, where we have discussed together the p-n junction under what's called the thermodynamic equilibrium. In the next part, my dear students, we are going to demonstrate the same p-n junction, but under what's called the biasing conditions. I mean, the forward bias condition, the reverse bias condition. What we are going to see is the impact of having an external bias on the energy band diagram, the carrier concentration, and how we can plot what's called the JV curve for an semiconductor p-n junction. This is the termination for part number 1, lecture number 2, dealing with semiconductor devices p-n junction, and see you in part number 2 next week, inshallah. Bye bye.